All right, good morning, everyone. How are you guys doing? How's everyone doing? You guys sound energy sapped. I expect you to be more energized. How many of you were at the football game on Saturday? Nice. Wasn't it an awesome victory? At some point, I thought they should have been with the mercy rule.
They did. They cut the second half down. Third and fourth quarter only 12 minutes each. The refs were like, "Look, this is really sad." So they approached David and they approached SC State coach and shortened it.
That using all quarterbacks.
Really? Oh my! So they shaved 3 minutes off of each of the quarters.
Yeah.
Has that been done before ever?
I don't know,
I read
but
an
I'd like them
article.
to
There
do it
was
again. It was
two in the past, like 2 instances of it in like the past like 5 years that were notable.
That's so embarrassing. Oh man. Yeah, but it was definitely good. So we're ranked what now in the polls?
5.
Still 5.
We're still 5? Boo.
But Louisville moved up to 3 because that makes sense.
Yeah, okay. I guess they expected us to be. Okay, no, that's good. This is really good. Did you guys get any ideas about economics while you're watching the football game? Yeah, you did? No ideas about economics? So what about could we use the tools of economics to rationalize or understand why they invoked the mercy rule?
Cost benefit analysis.
Okay, let's go with that cost benefit. Explain. What are the walk us through the cost benefit analysis. Can you say it louder?
They're mitigating injuries.
Who's mitigating injuries?
Both teams.
Okay, they're mitigating. And but why wouldn't you cut every game short?
Because those they cut off 3 minutes, so 6 minutes in total. And those 6 minutes, if you're really good and have luck, you could score enough to win the game.
Okay.
What's $300,000 divided by 6?
Say that again.
$300,000 divided by 6.
Oh, 50,000.
So that's how much money that South Carolina State was paid that they did not earn. They were paid $300,000 to play the game. Got 6 minutes out of it.
Okay.
So we paying them excess. Everybody's sitting in the stands paying out some money for tickets that didn't get their full value.
So why weren't there riots in terms of, because, what you're arguing is you're saying that from an economic standpoint, South Carolina State was incentivized to cut the game short because, so for Clemson, we're going to win anyway, so why don't we mitigate the injuries? And then for the South Carolina, and I'll come to the second, for the South Carolina State, what you're saying is that, look, we're getting paid $300,000 just for showing up. It doesn't matter if we win or not, we're clearly going to lose. So why should we not spend less time on the field mitigating injuries and make the same amount of money and get a higher kind of per unit time earnings?
Well, also I was kind of going thinking about the 300,000, from Clemson's standpoint. SC State, there's gonna be a point where their team is I do not want to show up anymore at Clemson, and Clemson's just gonna have to start paying them more and more to show up, right? So it's that's another cost for Clemson. I feel is if they beat them by too much more, then they might have to pay more than 300,000 to get them to come next time.
Oh, I see. This is interesting. So in a sense, it's you're saying that SC State is a punching bag, and it's okay, if I want to punch up on you next time, then if I really destroyed you the first time, you've lost so much respect that you need to be super well compensated in order to come and be a sucker for me in the future.
Yeah.
That's interesting.
Wouldn't that ship kind of have sailed though? I think over the past 4 games we've beat them, we've outscored them 238 to 20 over the past 4 or 5 years.
Okay, so
I feel this year was especially bad.
right,
Oh yeah.
right.
Last year was especially bad.
What was the last one?
Every year is especially bad.
But this is.
All right, 2 things. Number one, $300,000 to play us, a team that just was in the national championship game. That's a good deal considering that CSU played Alabama last year for 500 or 750 grand or something. They paid CSU in Charleston Southern. And then the other thing is what we get out of the 50,000 that SC State earned but did not really earn, in theory, means that we value mitigating injuries to Deshaun Watson more than $50,000 basically.
Okay. So this is useful. So you see how you can use economics to understand sports? Well, like just anything. It's just a way of thinking. It's kind of like, okay, what decisions do people make? And then under what circumstances can we rationalize those decisions given their incentives, right? Good. So when Miami beat the Spurs, you remember that game 6 where the Spurs were leading by 7 points and there was like a minute left and a lot of the Miami fans exited?
Yeah.
Right? So this is like kind of like the opposite of that. And then Miami came back and won, and they were trying to get back in, but the doors were locked. So you may ask, well, why did we spend the last 5 or 10 minutes like going down this kind of like alleyway? The purpose of doing this really is to get you to recognize that the point of economics really is to help you to build intuition for understanding the world around us, understanding how people make decisions, what are the incentives, what are the costs, what are the benefits that they face, and what are all of the different components of those costs and benefits. We came up with a lot of very interesting ideas, right, just by talking about it. And as a professional economist, this is what happens a lot. I have an idea that I get from observing the real world around us, and then I think, well, okay, cool, let me talk to some economists about it. And we figure out what are the costs, what are the benefits, what are some of the margins along which people can adjust, substituting in your second string quarterback with first string, et cetera, et cetera. And this is the kind of lens that I want you to take into the rest of the course when we start to read papers and to start to think about how do we apply the techniques that we've learned to understanding the market for education. So what I'm going to do is we're going to pick up where we left off last class, which was looking at regression analysis. Let me take just a minute or two just to kind of put into words what we were doing. So we posited that there's a relationship between how much schooling someone gets and the wages that they get, right? And then we said, well, what's a way that we can measure that relationship if we had data? And so before we jumped into the model, we actually said, well, okay, let's look at a particularly easy case where we can see that it's just the wages are increasing linearly with respect to an additional year of schooling. And we can clearly tell from that case for every additional year of schooling, log wages increase by 5 units. And then I said to you, well, there's a way to look at the relationship between the underlying data and the covariances and the variances of those data to figure out exactly how could you get the returns to education. Right? We got the same number, which was 5. And a lot of you were like, well, what was the point of what was the point of that? And the point of that really was, in some cases, you're going to have a lot of data points, and those data points may not all fall on a straight line. And so then the question is, what are some of the assumptions that you can make for estimating the relationship between one additional year of schooling and the percentage change in wages? And so then what we did was we talked about drawing a line of best fit through the data, which is exactly what an ordinary least squares regression estimate will do for you. And then we talked about the process of doing that. And so what I'm going to do is I'm going to pick up where we left off the last class, and I'm going to start from like the top and just kind of go through it again, because this is actually very important for you to understand what's going on here. And what we will do after that is we're going to talk about what are the assumptions that are needed for this line of best fit to make sense. In particular, what we're going to focus on is what happens when there's something that we don't observe, like what's something that we may not observe about an individual that affects wages. Ability. Exactly. If we don't observe ability, how does the fact that we don't observe ability affect the way in which we estimate the wages? And then we'll talk about some instrumental behavioral strategies which will allow us to get around them, right? Okay. And this will set us up for Thursday. So on Thursday, we will be in the lab, the Econ lab, to go through Stata. And so I'll send out a tutorial for Stata. And this was done by Princeton University, so which you get to open up Stata and just kind of work through it to build up your toolkit. Because a key component of this course really is giving you the tools to understand the way that economists think about education, and then to take that understanding to data so that we can measure things that are going to be very relevant for policymakers, and also for individual students who are making decisions about education. And then we can have a very informed discussion about what are the decisions that are being made.
Do you have work for this week?
Yes, we have homework for this week. Aren't you excited? You're not excited? Why aren't you excited about homework?
Because I'm not over it.
Oh, do you do any sports or like lifting or anything like that? When you go to the gym, are you like, man, this is gonna suck? Like I'm gonna like beat my bench like record.
So,
Why not?
it's enjoy it.
Because you're getting stronger. And this is the same thing too. Like the more homework you do, the stronger you get. Okay, good. I thought that was going to go over so much better. Okay, so this might be recap for some of you with your last class, but I want to go through this. So in our simple model, because this is actually pretty important. And by the way, tell me this is going to be on the homework. Okay. So in our simple model, we have log wages are equal to alpha plus gamma SI plus epsilon I, where SI is the years of schooling. Alpha is the wages if years of schooling equals to 0. So that's expected wages for not having any schooling whatsoever. And epsilon I is unobserved factors that affect earnings. All right. So suppose we have data on n students. How would we calculate alpha and gamma? Right, so this is the question that we're going to ask, right? You have all of this data. Let's say we have the universe of data of everyone that's gone to, of everyone in Clemson. We can see if they went to college or not. We can see their wages. We just have like the whole tax record. And they say, well, what's the returns to going to college? And they ask you, Ali, how would you go about doing this? Here's a way that you can do it. So let me draw this picture. And this picture is going to be instructive. So the data will look like we will have wages for each person. We're going to have years of schooling. So we have these two bits of data, right? So we need wages and years of schooling. For each person. And I'll just put here I equals 1 to n. Don't be afraid of n. N is just, n can be 50, n can be 100. N of this class is about 32. So don't be afraid when we use symbols. Like, you're getting stronger with manufacturing symbols. So our data may look something like this. Let's say this is the years of schooling, and this is the log wages. Our data could very well look something like this, right? But I'm just going through this as a review because I really want to make sure that the concepts stick with you. Because typically you might take a few lectures to go through this in your econometrics class, but we do it at just one lecture last class to go through this. So please feel free to ask questions. Okay, so let's take this for example. Let's say this is the wages of Tom. Is that okay if we put the wages Tom? All right, good. And this is the level of schooling that Tom has, right? And so this level here is what? What is this y star here? Who can give me an interpretation for this level of this predicted level of wages. What's this?
That's the vote.
Say that again?
That's the vote.
Well, what, okay.
Oh, it's like the point of
Uh-huh.
business school and average wage.
Exactly.
Those are equally.
So this wage here is what, these are the predicted wages for somebody with Tom's level of schooling, right? And so does Tom make more money or less money than we predict? Tom makes more money. Tom is a boss. You should be like Tom, right? And so this here is the epsilon I for Tom, right? This is epsilon for Tom. So these are the unobserved things about Tom that affect his earnings. And that explain why Tom earns more earnings than we would predict just from looking at how many years of schooling. So it might be that Tom has a really cool hat, or Tom is super smart, right? Or Tom had a really great business idea while he was at Clemson. Everybody understands that? Okay. Now we can take someone else here. Let's call this Mr. Y, Mr. X. No, we always use X. We're going to call this person here Mr. T. Oh, Mr. T. I think you guys are too young to know about Mr. T. So this is ST. These are the wages for Mr. T, right? And this is the actual wage of Mr. T, and this is what? Yeah, this is the expected or the predicted wages for Mr. T. And what can we say about Mr. T's epsilon?
It's less than expected.
It's less than expected. So we underpredict Mr. T's epsilon, Mr. T's wages, right? Because there's something observable about Mr. T that we can't see. Maybe it's that Mr. T has like, he wears tank tops, right? And employers don't like tank tops because they think you should cover your arms. You have the right to bare arms, but not to having bare arms, right? And so that could be what's happening with Mr. T. And because in the data, the only thing that we observe is what? Schooling and wages. Unless, we don't have any way to capture the fact that Mr. T always wears tank tops. And the job may require for Mr. T to look more professional like Professor Blair, right? Okay, good. So we're gonna underpredict Mr. T's wages. Now, we could alter this, and we could say, look, we think Mr. T is very cool, and we should totally get Mr. T's wages right. Like, because Mr. T is the man, right? And we can say, instead, we want to draw this line that gets Mr. T's wages perfectly, right? And we can say, all right, we can do something like this here, right? And what will be the prediction error in Mr. T's wages from this regression here? 0. And we could just make this totally about Mr. T. Well, what's the prediction error for Tom's wages now? It's huge, right? Because we just really want to capture the fact that Mr. T, we don't want to screw Mr. T's wages, but we end up totally messing up Tom's wages, right? And so depending on, and this line here is going to be determined by alpha and gamma. Gamma is going to be the slope of this line, and alpha is going to be the intercept of this line, right? And so in this case here, if we want to get Mr. T's wages correctly, alpha is going to have to be what?
Negative.
Alpha is going to be negative, right? And so we're going to predict that somebody that has no years of schooling is going to get negative wages. Does that seem like something that's sensible? No. Right? So there's something that's wrong with that. You have a question, Tom?
Yeah, question. For the simple model equation, is that the same as like econometrics equation as like B dot or B0 plus B1 xi?
Yes, that's a good question. So Tom is asking, I think in the past we used betas with the Mensa regression. Tom is asking, is this the same? Yes, it is the same. Because what's going to give this gamma an interpretation is the relationship between gamma and wages. So remember when we took the derivative of log wages with respect to schooling? And then we got 1 over wages times PhD schooling is equal to gamma. And then we rearrange that to show that gamma is the percentage change in wages for an additional year of schooling. if we call this gamma or beta or theta or whatever the case may be, does the interpretation change? No. So these are just labels. These are just completely labels. There's this great line in Romeo and Juliet. How many of you guys have read that when you were in high school? No, only 2 people? You guys have, don't be ashamed, it's okay to read. where Romeo has, is it Romeo where he's at Juliet's window, he says, what is in a name that if a rose if called by any other name would be as sweet? Right, you remember that? She's like, oh. So this is kind of like the same thing. What's in a gamma or beta? If called by any other name, it would be as sweet.
It's an impressive comparison.
And so the whole point of it is that it doesn't matter what we call it, right? Like what determines the relationship or the interpretation is the fact that this equation is linear and gamma. When we had the experience, it was quadratic in experience, and that affected the interpretation of the betas. Okay, so we just had a moment. That affects. So what affects the interpretation is kind of what's the explanatory variable, the s and the x that's there. If the x is a log on this side, or if it's a linear thing, or I feel like we need time. Right, okay. We all get that point, right?
Yeah.
Okay, good. This should be end of the term. What if we call the gamma R for roots? With the choose the interpretations. That'll be our inside joke in class. But anyway, the point is we can choose. So the only thing we have so far is the data. And we have to make a choice about gamma and alpha to figure out. So we can say, we want to perfectly predict Mr. T's wages, and we can get this one. Or we can say we want to perfectly predict Tom's wages, right? And we can go, and then we would screw Mr. T's wages. And so these trade-offs that we're making, right? And so here is one metric that we can use that's going to be a reasonable metric. I'm going to draw this graph again because that's going to be helpful. So, and I really want you to understand this. I'm going to take my time as I go through this because was the pace of last class decent? Did you feel like there was sufficiently, it wasn't too fast? Okay, what about this lecture? Is the pace decent? Okay, good. Please feel free to give me feedback on that because it really helps a lot with that sort of stuff. Because there was one brave soul that came to me and said, look, the class was going too fast and I slowed things down and everybody benefited. So you be that brave soul. Okay, so again, let's look at our data. Let me draw my data more systematically. Okay. And what we're going to do is we're going to propose, this really goes with the Romeo and Juliet theme. We're going to propose alpha hat and gamma hat. These are going to be, we're going to say, well, what if we were to choose alpha hat and gamma hat to be our predicted, to be our values for the returns to the rate of return to schooling and the expected earnings given that schooling is equal to 0. And then we're going to ask the question, how bad would our prediction be? For a given gamma hat and a given alpha hat, how bad would the prediction be, right? Okay, so let's say that this is our line. So that's going to mean that this quantity here is going to be what? What's this going to be here? So this is not equal to 0. So what's this going to be here? Alpha hat, right? That's going to be alpha hat. And the slope of this line, so d log wages, s is going to be equal to what? Gamma hat, right? And we can choose whatever values we want to do. We have not picked the values yet. But what we want to do is we want to set up a criteria for picking these values. So let's take this first point. So for this first point, this is going to be the prediction error here. So this is epsilon 1, right? This is going to be epsilon 2. This is going to be epsilon 3. That's just the distance between here and here, right? This here is going to be epsilon 4. Erase that. epsilon 5 is going to basically be 0, right? And we're going to have epsilon 6. And then this here is going to be epsilon 7. So you can see that, right? And if we were to change alpha hat, all of these values are going to change, right? We can better predict epsilon 1 maybe, but then we can do a worse job of predicting epsilon 2 and 3 and so on and so forth. Everybody understands that? So far this is just a proposal. Okay. So let's define the sum of the square residuals. And I'm going to reduce to SSR in the following way. We're going to take each of these residuals, which represents a prediction error, and we're going to square them. And the reason why we're going to square them is because if we did not square them and we just added them up, if you had a situation where you had as many lines on top versus on bottom, you can have a situation where the prediction error, the overall prediction error is 0, but then it's still a very bad prediction. Does that make sense? But when we square them, what's going to happen is we're going to penalize you for being over-predicted, but also for being under-predicted as well too. Does that make sense? Okay. Does anybody have a question on that? Okay. All right, great. So let's define that in the following way. We're going to say that this is 1 over n. So this is going to take the average. There are n data points. And we're going to sum. Everyone knows that this big sigma is the sum sign, right? This is going to be the sum from, actually let me write it out first. That's probably better. So we'll do 1 over n times epsilon 1 squared plus epsilon 2 squared plus epsilon 3 squared plus dot 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 plus epsilon n squared, which we can simplify. We can simply write that as 1 over n, the sum on epsilon I squared from I equals 1 to n. These are the same thing, right? And if this quantity is large, what does that tell us?
It's not a very good predictor.
It's not a very good predictor. Why is it not a very good predictor if that sum is really large?
Because a lot of the data points aren't very close to the prediction.
Exactly. But what if that's very small? What would that tell us if the sum of the square residuals is very small?
It's a very good prediction.
It's very good. And why is it a good prediction, Tim? I mean, Tom, sorry.
Because it's closer to the regression.
Exactly. And so in the case of the example that we used last class where we had just a linear line, right? We had everything was lining up completely perfectly, right? We had a situation where we had, it was like, the data points just looked like this, and they all lie on a straight line. And so the sum of the square residuals for this one would have just been 0. And so if we chose a line that was like this, it would get the average right. So if we chose the line that was like this, it would get the average right, but then these extreme points would be completely wrong. Right? But if, yeah, this is actually a very good example. So let's suppose we had something that looks like this. Right? Where this was 0, this was 1, this was 2, and this was 0 here, this was 1, and this was 2. And again, this is not what it is, and this is the years of schooling. The prediction error here is going to be +1. The prediction error here is going to be -1. And so if we were only to take the average prediction error, we would get, and the prediction error here is going to be 0, we'd get -1 plus 0 plus 1, which would be 0, right? There would be no aggregate prediction error there. But because if we were to square instead, we would get 1 squared plus 0 plus 1. And so you see how squaring it allows us to capture whether the line is a good fit line or not. Whereas if we didn't square it, we wouldn't see that. Your question?
No.
Okay. All right, you look like you're deep into that. Does that make sense? No? Your question?
No.
It's okay to ask questions. Okay, that makes sense, right? Everybody understands why we're taking the sum of the square residuals? Okay, good. You guys, questions over here? No? Okay, perfect. All right. Okay, good. So this is our sum of squares residuals. And what we want to do is, so this is a comment. The smaller the SSN, whoa, no, SSR. The smaller the SSR is, the better our values, our proposed values of alpha hat and gamma hat fit the data. Everyone get that? So we have all of this data that Clemson University and State of South Carolina has given us, and they say, look, tell us how valuable going to college is, right? And then what we do is we say, okay, we can set up this empirical framework here, and we can use this, we can use the data to estimate alpha and gamma. And so what we do is we say, well, suppose alpha and gamma is given, has a particular value. How well does that fit in the data? And then we can look for the alphas and the gammas that are going to give us the best prediction. And in particular, it's going to be the alphas and the gammas that are going to minimize the sum of the square residuals. Everyone understand that? Okay. So, the values of alpha hat, gamma hat that minimize the sum of the square residuals will produce our line of best fit. Right? Moreover, this is called an ordinary least squares regression. And this is OLS. So the squares is going to come from the fact that we have the sum of the square residuals, and the least squares is going to come from the fact that we're going to be minimizing the sum of the squared residuals. And the ordinary part is coming from the fact that we don't have any special weighting on the sum of the square residuals. Because in particular, what we could do is we could actually say, there's certain residuals that we want to predict really well. Maybe we want to make sure that we minimize the prediction error for folks from the low country, because we have a policy initiative where we want to make sure that people from the low country, we're not underestimating the returns from them. And so we may have a social planner's preference for like not under predicting their weight.